Okay. So I want to give you an update then on our efforts to try to model reconnection in MRX, this experiment at Princeton. This work here is done primarily by my postdoc Vadim Reuterstein in collaboration with the usual suspects at Los Alamos. Seth Dorfman is a graduate student there at Princeton who originally got us working on this problem. He came to Iowa the last summer I was there and did this in the 2D limit and got us thinking about how we can try to model MRX within a fully kinetic simulation. So for people who haven't seen a picture of MRX, this is what it is. It's a toroidal geometry, I guess merging spheromax, I hear it called sometimes, where you have a toroidal current in these donuts, and as that current is pulled back down, you pull flux inward between them and create this a current sheet in between, that's the red, and they stick an array of probes in it and can take all sorts of measurements on the structure of the layer and the fluctuations that occur within the layer and upstream of the layer. Here's some typical parameters for MRX. We can come back in a minute. So what is our motivation? Well, of course, my motivation is to try to better understand reconnection, the structure of the reconnection layer in weakly collisional plasmas, and the role that instabilities play in setting that structure and influencing reconnection, or perhaps even just instabilities that might be useful from a diagnostic perspective for space plasmas. It's good to know which modes should exist where, and maybe they give you clues when you're looking at the space data. So lots of different simulation approaches. Why should we use fully kinetic PIC simulations for this problem? Well, most of the MRX discharges have very weak guide field, almost a neutral sheet type configuration, where the current sheets that are forming then, you really do have almost a null region where the electrons can have all sorts of complicated orbits. The ions as well can have complicated orbits within it. That if you look at the reconnection electric fields in the experiment, they're typically comparable to the Dreiser runaway limit, usually a little bit on the lower side of it. Again, fluid closures are not going to be very good as you approach the Dreiser limit. You really need kinetic mechanisms to self-consistently take over. And this approach I'm going to talk about, where we do fully kinetic and include a Monte Carlo treatment of Coulomb collisions, then can very naturally go between sub-Dreiser and super-Dreiser. I don't know any other approach really to do that. And so the instabilities of interest that I'm going to talk about here are in the lower hybrid range, and there's good reasons to believe that they can involve both ion and electron kinetic effects. The broader goal of this effort, of course, is to try to understand reconnection well enough that we can look at other applications in our solar system, in the magnetosphere and beyond, and say something useful from the physics we learn and study in MRX to better extrapolate it to the rest of our solar system. And hopefully by benchmarking kinetic simulations with a controlled laboratory experiment, the idea is that we can more confidently do this. But you'll hear from this talk, it's hard. So here's another motivation slide, that these instabilities that I'm going to talk about, there are electromagnetic instabilities that are in the lower hybrid range. People that have followed the MRX results, they know that these guys have been reporting these for 4 or 5 years now. This is from Hantao-G's PRL in 2004. That's the lower hybrid frequency. Theta is their toroidal direction. So there's power here along. I think this is the corresponding to the drift frequency due to their electron drift in the problem. There's the lower hybrid frequency. So they have significant power up to it, and then even beyond it in this figure.
So which direction is K theta again?
It's the current direction in the neutral sheet, the toroidal direction. Yes. And here's a paper from recent cluster observations from Zhao et al. It was published in GRL last year, where they also report electromagnetic fluctuations in the lower hybrid range as they cross a a reconnecting current sheet. So they claim they see these lower hybrid fluctuations clear into the central region of the electron sheet. And that the fluctuations there, if you read the paper, have similarities with the fluctuation that Hantau has reported and strong similarities to the fluctuations that I'm going to talk about. So it would be nice to understand what this all is and what role it plays in reconnection and when we should expect to see it and when we shouldn't. So that's what we're trying to do. So another part of our approach for this and trying to model it with fully kinetic simulations is most people who do fully kinetic simulations of reconnection start with a current sheet geometry where you already have your free energy and you let it go, either from a linear instability like a tearing mode in the system or with a significant perturbation to kick it off. In MRX, they're not initially starting with a current sheet. They form a current sheet by the process of pulling flux back into the flux cores. And since our broader goal is to understand the structure of the electron layer that's here, we thought it might be fun when Seth came like 3 years ago to try to put up a global model where we can capture the process in which you're driving the sheet. Okay? For the question I'm going to talk about today, maybe it's not so crucial because we're focusing in on the waves that are there and the thickness of the layer. But I'm convinced that this can be an important issue if you start thinking about the length of the layer. I'll come back to that. I think your downstream boundary conditions and the way in which you drive it could play an important role in setting the length. So we have a conducting box where particles that hit the edge of the box are reflected. Field boundary conditions are conducting here. Then we have these circle cutouts. Particles that hit this, we can pick any boundary condition we want, from reflecting to absorbing. Inside the circle, we have a current that we prescribe as a function of time to match the type of drive that's in the experiment. So then I'm showing two different versions of this. This is what we would call our global, although it's just in Cartesian geometry. We're not trying to model the full toroidal effects here. This is just a slab box, and if it's 3D, then it's always periodic in this direction, and we're picking the size of the box in the y direction to allow some spectrum of waves. Okay. Even this is challenging if you're trying to do a global simulation. It can be up to like 10 ion inertial lengths between the flux cores. If you did the whole box, maybe it's 25 or 30. Okay? So another version we use in 3D is to go ahead and chop off a smaller region from here to here, and then go ahead and make it periodic in that outflow direction as well. So we have a smaller volume of plasma we're trying to capture. We can go to higher mass ratio and try to drive the instabilities there and look at them. Okay, so here's some pictures from the simulations that Seth did back in 2007, just showing you the basic idea. We started in the 2D collisionless limit, and this was with my old PIC code. As you pull the flux back into the flux cores, you create a current sheet in between. This is the electron fluid velocity in the out-of-plane direction. So we basically did this over a whole range of mass ratios, a whole range of drive strengths, and the quantity that we were mainly focusing on there was the width of the layer. So this is zooming in and looking at these electron outflow jets that are developing. And we tried to measure the width of the layer the same way that they say they're doing it within the experiment. And what's that?
You have a little bit of asymmetry at the very end of the simulation.
Yeah, you definitely do. I mean, it is a pixel.
Layer interacting with the current.
You can see at the beginning part of it, the layer stays quite short, like almost a current spike. During that period of the simulation, you have a very steep pressure profile approaching the flux core. Okay? But then a lot of the plasma gets absorbed near the flux core, and the pressure profile starts to relax, your current sheet extends, and in many of these, then you'll form a magnetic island at late time as you get an elongated electron sheet. Okay, in a PIC simulation, you don't have to maintain symmetry, right? There's random numbers all over involved in it at late time. What's that? In terms of the ion cyclotron frequency, these simulations went from like 100 to 500, kind of in that range, as we varied the ramp down time on how hard we were driving them. So this was sort of the key result from it. If you went in, measure the thickness of the layer, normalize it to the local electron skin depth, and try to look at this as a function of mass ratio. If you extrapolate out here to hydrogen mass ratio and beyond, they have hydrogen and deuterium and helium is the experimental data up here, that it looks like you're way below what they've reported previously as the thickness of their layer. So that's a motivation to go beyond the 2D collisionless limit. The main ideas that might be broadening the layer is either Coulomb collisions, which we're not including here, or perhaps plasma instabilities develop with a K-vector in this out-of-plane direction and lead to turbulence within the layer that broadens it. So those are the two ideas that we wanted to explore. We sort of did it step by step over the last couple years with this VPIC code, which, as I already said, has this Monte Carlo treatment of the collision operator, which we have benchmarked against Brzezinski transport theory in certain limits for the parallel and perpendicular resistivities, as well as the thermal-electric terms, which can play a role on the edge of these layers in the momentum balance, actually.
One question, Mike. You have the slab geometry.
Yeah.
So did you match the currents in the conductors or the reconnection electric field to drive? Like in the toroidal system, you get a different, you change your current by 1 ampere, you get a different amount of flux in the toroidal system compared to a linear system. Like the self-inductance of a loop in the toroidal system depends on the radius, because you don't have that in the linear system.
Well, when we match, we're matching everything in dimensionless units. So if we make a dimensionless reconnection rate, like we always do, we try to match that. And it's not we just match it at one point. We've actually scanned it over a fairly sizable region where we can.
Rather than the coil current.
That's right. I mean, to do the problem, you really do have to scale it still. I mean, you're not doing this. You have to scale it in a couple of ways. Okay, this slide sort of says. I mean, these are the two parameters that would really kill you if you wanted to just do the physical parameters. Mass ratio you hear a lot about, and you understand why that's hard. But this one is even harder. The ratio of the plasma frequency to the cyclotron frequency. In MRX, that might be 80 or 100. I mean, there's just no way to do a PIC simulation anywhere close to that. So in 2D, we might make that 3 to 5 or something, implying that the plasma is a lot hotter. Well, then you'd have to make your magnetic field higher in order to bring your beta back down. So we're trying to match these. So the system size in terms of your ion kinetic scale, your drive time in terms of an ion cyclotron time, and some kind of a reference beta. And he already has kind of the range of values we're considering for collisionless. Now then, for collisionality, well, what do you want to match? One obvious thing is that you probably want to match this ratio of nu EI over omega CE. And in a lot of these two-fluid simulations, we think of this really as your dimensionless resistivity, so that if you wanted to know what the Lundquist number of your simulation is, it's like a system size over an inertial length, and then you have this factor. So if I am matched my system size in terms of an inertial length, and I match this parameter, then my Lundquist number is in the right ballpark, which is, I mean, seems something obvious that you would want to match, at least when you're in the collisional, or if you want to consider this transition between collisional Sweet-Parker type regimes and these kinetic regimes, because the ratio of this, of the Sweet-Parker thickness, the resistive layer to the ion inertial length, it's going like the square root of this system size times this resistivity. But there's another important collisionality parameter, and it's not really possible to simultaneously match them, and that's the ratio of your reconnection electric field to your Dreiser runaway field. And it turns out you can't simultaneously match them both unless you really are using the physical mass ratio. So both of these we're scanning over some region, trying to look at scalings and see if the physics we see in those scalings are consistent with the physics that they're seeing in the experiment.
How much different is the Dreiser criterion compared to the Lundquist number criterion? Is it a lot different?
It's not hugely different, because it's coming in with the square root, and our highest ones are, it's a square root factor, and we're up to like mass ratios of 300 or 400. So
So it does, the difference does come in as some fraction of the mass ratio?
it does, the way we're looking at it. Yeah. So with our artificial mass ratio, it's easier to push it into runaway than it would be at a hydrogen mass ratio. The higher your mass ratio you get, you open up a window, at least the way I look at it, where it's possible to break this condition but still not be runaway yet. So that's the regime where it seems like a two-fluid closure has the best chance of working properly. But we've kind of shrunk that with our artificial parameters. So again, then Vadine had a paper that came out just this year. He's using the same boundary conditions that Seth Dorfman came up with. And here you just zoom in on a window. Here's one of his collisionless ones, an example of the collisional one. So he's zooming in on these layers and doing an analysis of it. And I just give you a couple slides on what the key results are. That this is looking at the generalized Ohm's law, or the electron momentum equation, and asking which terms are most important near the X line as you transition between regimes that are very collisional to weakly collisional regimes. So since you're near the X line, this piece is small, and as Jim just discussed yesterday or Wednesday, that's small and that's small. In the collisionless limit near the X line, then you're mainly balancing E with div PE, okay? And as you, of course, go into a very collisional limit where kinetic effects aren't important at all, that you should balance E with your momentum exchange, which is the first moment of your collision operator. Near your X line, there's really no thermal electric term. It's really just your friction force that's coming in. And so if he plots this as a function of, he's looking at how big is your collision operator term in comparison to your non-ideal term. In other words, what's breaking your frozen in condition near the X line as a function of EY or E crit. So if EY is much less than the Dreiser runaway limit, he's coming right back up here to the fluid limit where you're balancing most of it through collisional momentum exchange. If we compare what we're actually getting in terms of real units and comparing it to Brzezinski expressions, we've shown in previous papers we published the year before that we're coming very close right here in the center of the sheet. As you start becoming comparable to runaway, there's a sharp drop off, and you end up balancing about 90% of the electric field through div PE. You can see it sort of saturates here. It doesn't keep going to zero, or maybe the slope's slightly weak. I mean, slightly negative, but I don't quite understand that. What's setting that saturation level? Okay. Then if he goes in and, first of all, he did a huge number of simulations trying to think about exactly how to present to get his hands around on how to think about what collisions are doing to the thickness of the layer. Because you see weak dependencies on the mass ratio. You see weak dependencies on how hard you drive it or how quickly you're pushing this flux in. You see weak dependencies on exactly how you pick your reference beta, and a lot of other things. But this is a way that Vadine came up with that essentially collapses all the simulation data onto a single line. And the argument, I think, goes something like this, that if you really are in the collisionless limit, that the thickness of the sheet, the physics that sets the thickness of the electron layer are these bouncing orbits for neutral sheet geometry. And the order of magnitude of those, if you go just upstream of the electron layer and compute a gyro radius based on that magnetic field, the thickness should be a few times that. Okay? And that's what people have said for many years here. So if he normalizes his measured...
Say that again. You base it on the temperature where?
Well, the temperature doesn't change very much. The magnetic field does. I'm saying if you look at what the magnetic field is just upstream of the electron layer, and you compute your electron gyro radius based on that magnetic field. Right, that's what rho E star is.
How do you use your temperature though? Because that's one of the things that we've always claimed, and that is it really doesn't matter what the upstream temperature is, because once you get into the layer, Particle.
I think
counterbalance.
for these estimates, he's just taking the temperature at the center of the layer.
Okay, well, that's good.
Yeah.
That's good. Because that can be very different than upstream.
Okay.
Yeah. So that's good.
But it collapses everything. If you push it weaker and weaker collisions, completely collisionless, it doesn't really matter then how hard you drive it, exactly what the mass ratio is, or anything. It's just like, well, that is the physical scale that's setting it. That's what we see. But then as you come back here to be more collisional, it starts coming away from that. I guess that's not too surprising. But it's fairly slow here. This is where the experiments claim to be in this phase space of the sheet thickness over this rho E star is a function of this runaway field. And I mean, you're still way away from it, is the point here. Vadim put in this comparison. If you compare the sheet thickness to rho E, and you assume that you become really collisional where E is balanced entirely by resistivity, it turns out then you can write this ratio like this, just in terms of an E crit over E, and there's a beta factor here, where that beta really has to be of order unity. It's the beta based on the edge field and the central temperature just from force balance. It sort of has to be in this range, or otherwise you can't balance, you can't create an equilibrium across it. And that's this sort of his shaded line for this region. So he would say this is the uncertainty in beta, and it doesn't look like any way you can get up to the experiment there. So what are the other possibilities to reconcile the discrepancy? Well, the one that's mentioned a lot is the 3D instabilities and turbulence, and that's our motivation for going forward in 3D. Vadim listed a few other possibilities here that, what if there's more neutrals? Maybe that could broaden it. What about the probes, or sticking a bunch of probes in there? Can that have any influence? And then maybe there's other things you could add. So let me then go to these drift wave instabilities, this lower hybrid drift. And first review in just 4 or 5 slides what we know about the lower hybrid drift instability just within a Harris sheet. 2D Harris sheet geometry where we don't allow reconnection. It's a problem I studied a lot 6, 7 years ago. And the basic body of knowledge about these modes, these are unstable drift waves. There's a coupling to lower hybrid waves. They are driven by diamagnetic drifts in low beta plasmas. They tend to want to have K parallel equal to 0. The fastest growing modes by far are mostly electrostatic with a small electromagnetic piece to them, and they have Ky rho E of order unity. And there's really, in fact, a broad range of unstable modes in the lower hybrid range, from these fastest growing modes all the way down to longer, more electromagnetic modes. And basically, the way I view this is if you have thicker sheets, all of our simulations seem to show that for neutral sheet geometry, these fast-growing electrostatic modes are stuck on the edge of the sheet. They can't penetrate into the high beta central region. You can understand it from dispersion relations. There's been a huge body of work from Ron Davidson and Joe Huba, Jim Drake. So it's pretty much all mapped out. Anything you would want to know about these modes is in the literature. But if you go to these very thin sheets where you start going below the ion gyro scale, in my research I found a longer, more electromagnetic mode that has a characteristic wavelength that's intermediate between electron and ion scales. And this definitely penetrates into the center of the sheet and causes strong distortions to the layer. And so it's been my goal for a long time to understand if these really occur in 3D reconnection geometries and what they might do. And to do that one of the things I did was an exact linear theory of this problem. It's very tricky to try to do a good linear theory of these modes for a variety of reasons that I don't want to get into. But my approach then is to say, well, let's just develop a numerical approach to the problem where we're assuming a general perturbation. We treat ions and electrons both with the Vlasov equation. We solve the orbit integral numerically using these exact funny trajectories. And we solve the integral differential eigenvalue problem with just a finite element method. So we've used this extensively over the past 10 years to interpret what we're seeing in the PIC simulations. Here's an example from this for the short wavelength mode. This is a ky rho e equal to 1 mode. Here's the electromagnetic part of the perturbation. It perturbs AX, AY, which means that just BZ is perturbed. And it perturbs your electrostatic potential. And you can see that in the center of the layer, you really don't pick up anything. These modes are living on the edge of the sheet with a real frequency in the lower hybrid range and a growth rate that's some fraction of the lower hybrid range. Here's a simulation from 6 or 7 years ago that I showed where you're picking up this lower hybrid turbulence on the edge of the sheet, where it really can't conceivably cause anomalous resistivity in the center near your X line that you really care about. So here's an example of a longer wavelength mode that has ky square root rho I rho e of ordered unity. Now you pick up an electromagnetic piece to the mode that's really localized about the center, some fluctuations here on the edge. And it also has an electrostatic piece to it that looks very much like the previous eigenfunction. The electrostatic part of the fluctuations are more confined to the edge of the sheet. And it's debatable whether you really want to call this a lower hybrid mode or not. We always did because it's in the lower hybrid range and has many of the same features. The phase velocity is in the same ballpark, propagates in the same direction. The electrostatic eigenfunction looks very similar to the shorter wavelength mode. But how did it get all the way in the center? We don't know for sure. Maybe it's some kind of a tunneling effect where the free energy on the edge of the layer eventually tunnels across your sheet and creates a global eigenmode. That's one idea we've batted around. Here's a simulation then for hydrogen mass ratio 2D hair sheet geometry. And you see all the fine scale lower hybrid turbulence on the edge. Then you see the shorter wavelength lower hybrid mode develop. And at the end, you see even a longer wavelength mode, equal 1 mode, I guess. Let me play that one more time. This intermediate scale one is like a mode 5 or 6 or something. You'll see the little red wiggles here. This is where it's essentially kinking your current density at this characteristic hybrid scale between the ion and electron. Here's an example for weak guide field that I just did for you, Lynn, a few months ago. They were trying to do gyrokinetic simulations of this. The guide field here is 0.2. It's hydrogen mass ratio. She told me what range of wavelengths to look for, and I pulled off a mode that was, again, right in this characteristic scale, and made a prediction then for the growth rate and the real frequency for this mode. And here again is the simulation. This is JY and this is AX. You go back and look at the parity. AX was supposed to be even. The perturbation was supposed to, again, give a kinking to the layer, and it does. If you compare back with the linear theory and look at the growth rate of this m equal to 2 kinking, and compare it with the linear theory, it's right on. If you go in and look at the phase velocity and pull off a real frequency, you can do this to really high accuracy if you just follow an individual mode. Again, it's right on what the Vlasov code would expect. So there's no question these exist within hydrogen plasmas if you make the layer thin within 2D hair sheet geometry. The question is, though, that in 3D reconnection geometry, you very quickly evolve away from a hair sheet. In MRX, you never really have a hair sheet. You're trying to self-consistently form a layer as you drive it away from an X point. So you may never have a hair sheet. So does it really exist in reconnection geometry? And that's the last part here.
Does this thing get stabilized by strong guide field? If I increase the guide field, does it go away?
I would think so. But we've never really explored the strong guide field limit that Jim was talking about. It would be very interesting to go to stronger guide field. This, in fact, is not the fastest growing mode. As you add a guide field, the fastest growing mode actually rotates. It likes to have k parallel equal to 0. So it becomes intrinsically 3D as soon as you add a guide field, that you'll have pairs of modes that are slightly rotated. And they'll rotate more as you add more guide field.
Question.
Yeah.
In addition to the lower hybrid drift type modes, people have been talking about beam modes. What are beam modes in this context?
I'm not sure.
When I say people, I'm cultivating G.
Yeah, I know. They have some analytic theory, and It's Yansong, Yansong Wang working with Russell Calderon. They have something called the beam mode, and I've exchanged a number of emails with Yansong just in the last few weeks. Yeah, and I don't really understand how those beam modes fit in with lower hybrid drift. So here's a frequency spectrum. The omega is a function of k, where the blue stuff here is just the power density from one of these PIC simulations. The solid line is from the linear Vlasov code, where I'm trying to go in and find the fastest growing eigenmode at a particular k. It's very tedious because for a given k, you actually have a spectrum of unstable eigenmodes. Trying to find the fastest growing one and tracking it as a function of k is tedious. But if we do that, it seems like these short wavelength traditional lower hybrid modes seem to fall along this same branch as these longer wavelength ones. That's another reason why I think, unless someone can correct us, that it's fair to call them a long wavelength lower hybrid node. So it's very strong in a Harris sheet. Again, this is hydrogen mass ratio with the sheet thickness over an electron gyro radius of about 10, so below the ion scale. If you go ahead and calculate this anomalous drag coefficient that Jim put up in his talk, as soon as you start seeing the electron layer become strongly distorted, where the kinking is really warping the layer, that this ratio, when you average over the y direction for our averaging, just like Jim was doing, this ratio starts to shoot up. And he's getting 60% or so. So it's big anomalous drag if you can create the instability and have it survive in reconnection geometry. So 3D. So Vadim coded up these boundary conditions in VPIC in 3D. I'll just show you one movie and then I'll go into the results. Here are the flux cores again. So he's really driving the reconnection process by reducing the current in these flux cores. The colors here are the ion outflow, and there's some sample magnetic field lines here. And what you're going to see in the movie is that you start inducing the current. He's plotting an isosurface of a current density, and I think he may have colored it with electric field fluctuations or something. It's not too important. The thing is that you can sort of, looking at it sideways, see that there's a rippling in it. I believe this one too had some weak Coulomb collisions in the ballpark of what MRX would have. And so here he's doing these power density plots. The left-hand side is his magnetic fluctuations near the center. He's got a probe where he's looking at a time series as a function of time and as a function of the y directions. So he can actually invert the whole thing and compute omega as a function of k. So in the center, the important point is that he's seeing power right near this characteristic scale that we studied in Harris sheets. So the wiggling, I mean, we think it's fair to interpret this wiggling we're seeing in the layer is the same thing that we were studying in the simplified Harris sheet geometry, which is the same thing we had a Vlasov theory for. Here's the electric field fluctuations on the edge. And then, he has it in terms of k rho e, so you're seeing stuff come out to something on the order of k rho e. So here he's, I think, taking a vertical cut through the x line and summing over taking the absolute value of these fluctuations to show you how they're localized in comparison to the current density, which is red. So the fluctuations in the electric field are shifted. I believe that this particular one, he has a bit of an asymmetry in it, where he's trying to mock up the toroidal asymmetry that exists in MRX due to the toroidicity. Because of that, then you have an actual asymmetry in your current layer, and the beta is higher on one side than the other. So I think this is probably the low beta side, where he's getting more electric field fluctuations. But then again, these magnetic fluctuations are in the center. So the kind of profiles there look similar then to the kind of profiles they talk about on MRX. So then the last few slides is his attempt then to try to make contact with these results back to collisionless open boundary simulations, where he's picking an equilibrium, at least a
Wait a minute,
fluid.
can I go back though? So what's your bottom line? What's the current rate of friction? Did I
Yeah.
miss that?
Yeah, it's a little bit the ordering here. The bottom line is that you see the instability, the properties of the waves are, the wavelength is compares well with what they're saying. But then our waves are still very coherent. We see a very long coherence length in it. I mean, you just see it visually if you look at it. Where they claim the coherence length is very short. And then the bigger discrepancy is that maybe we see a 30 or 40% broadening to this rippling, but to get a factor of 3 to 5 that they want, we're nowhere near that. I mean, you just have to like completely roll the layer over where the kinking folds back upon itself. We have some examples that are close to that, where it looks like, you know, it forms a full vortice, and then that really breaks things up. But generally not.
But,
Yeah.
so there's one pseudo current layer effect, broadening effect, where if you take a kinking thing and you do like a quasi-linear average, you get a fake broadening.
Even the fake broadening is nowhere
Not
near.
sufficient.
No, because you just think about it, to make it 3 to 5, then you really have
Yeah,
to
you
do
really-
that. And you can't, in these, if you really start doing this, they actually roll over and break, some kind of breaking. And hair sheet geometry, very clear, you can make it happen. But in reconnection geometry, it looks hard. And he has the last slide will say the physics of why he thinks so. I mean, there's a couple physics reasons. So yeah, the flow of the talk is a little weird here. Because the dual goal here then is to say, you know, whether we see it in MRX and also whether we see it in, whether those results might be relevant to the magnetosphere. Another important thing about the MRX simulations is that if he does the initialization so that the layer is perfectly symmetric, you'll see these waves more early on when there's still significant density gradients. But as a function of time, those gradients tend to relax, and the mode seems to be getting weaker just from that effect. On the other hand, if you put in an asymmetry in your profiles, that does indeed seem to maintain the mode at a more vigorous level, even at late times. So here he's picking a profile that's asymmetric and might be relevant to the magnetopause, where I think he has about a factor of 5 difference in beta between the two sides. And then this is an open boundary, driven open boundary system that's completely collisionless. And he's done it up to mass ratios of about 400. And it's the same basic story. What you're looking at is a current sheet coming out of the plane. He's colored it with the electric field fluctuations. So it's definitely doing this rippling again, but still not completely breaking over. You've seen the spectrum. I need to show that again. This is important. I only have a few more slides. He's been looking at, well, okay, you see the waves, even if it doesn't completely broaden it, like we would want to see to agree with our MRX, it's still fair to ask, because they're strong enough so they're clearly visible no matter how you look at it. It's still fair to ask, well, what role does it play when you average a generalized Ohm's law over that y direction? So you average over the fluctuations. And that's one of the reasons he's trying to make the boxes longer and wide, to try to get some statistics there. I don't really need to go into this in too much detail. I'm doing exactly what Jim was doing, except the way that Vadim has broken it up is a little bit different here. We have our drag term that Jim talked about, which is really appropriately looked at as maybe as anomalous resistivity. It's what other people call anomalous resistivity. And then you have the other nonlinear terms that can come, and one of them is from averaging this, and the other is from averaging this. And that's essentially what he's showing here as a function of a cut, a vertical cut through the X line. And so the traditional red curve here, your anomalous resistivity, is maybe coming up to about 25% of your E naught. You're to balance 25% of your electric field near the X line. But it's not near the X line. The black dashed vertical blue line is actually where the X line is. So it's displaced away from it. So it's not even in the right place, actually, to balance it near the X line. If you go near the X line, then you're down to maybe 5% or so, which is a pretty small effect. On the other hand, if you if you look at this term, which is the nonlinear average of this, I believe Jim was combining essentially this term with the convective term over here and rewriting it as a stress tensor. And maybe we should be doing that too, I don't know. But the way Vadim did it, he says that the biggest piece near the X line is fluctuations that are associated with this, and that is coming up to about 25%. So maybe it's still interesting, maybe it's similar to the concepts Jim has been talking about.
Let me ask a really simple math question. Why, for example, take the average of that equation you've got up there rather than dividing the equation by n? So in other words, why would you prefer an equation for dp dt over an equation for dv dt? Right, this is must be some simple thing. Jim, can you explain?
I don't know, Jim?
Well, I did it because I think you want to write this in divergence form, so that when you average the equation, then you get,
You can bring the average through the divergence.
yeah, right.
Okay.
So I tried to have the whole thing in divergence form, and then there's a big term which is the divergence of PZZ, and I think you really want to completely annihilate that term. So that's why I wrote it, and the divergence form that I had listed the other day.
Yeah, now on the other hand, if you look at, well, what is the momentum balance out along the separatrices, we see that the drag term there can be order unity all along the separatrices. So these modes are playing a really big role along there. Trying to get it to work near the X line looks more challenging here for these low beta configurations. We wouldn't totally rule out, but it's not looking that promising to get it to work vigorously near the X line, like Jim was showing at the he was showing at low beta, we're at high beta.
Like what electric field do you balance in that simple electric field, right?
What's that? He's doing basically just the same kind of calculation, but further out along the separatrices. The same calculation as the previous.
Just the reconnect one, pretty constant.
Yeah, but there you also have in-plane fields that make.
Well, the fluctuations, I mean, you could do it in different directions, but it's trickier to do it in in-plane. We're trying to average over this symmetry direction. It's hard to do your averaging.
Well, so in other words, did you average, you're trying to balance E parallel rather than the inductive part itself?
Probably that would be better, but I think his averaging here is just in Y.
Oh, okay.
Like there you have huge parallel and perpendicular fields that point in Y as well.
Yeah, but that comes off as the V cross B term, so presumably he has that in there.
He should.
Yeah.
So we think part of the issues, okay, first of all, there's a large body of work on trying to look at these various instabilities in just hair sheet geometry. That's a great place to start to understand the instabilities and what instabilities can be there. But it's hard to take that work and directly extend it to reconnection simulations because your profiles change as a function of time and they may change away to something totally different. The other issue we think is that you really have to beat some kind of a convective transit time scale for these. That like the instabilities are sort of growing up in this region. He's just sort of roughly drawing a box. This is asymmetric again, and this is the low beta side. And then conceptually, the box is the region over which we see the mode to be localized. But you can quickly compute a time scale for all the plasma to be flushed out of this box. And we think sort of a condition you have to beat is you need modes that grow faster than that transit time scale. This is sort of the way he did it. He's assuming this is like 10 rho E, and he's assuming the current sheet is something on the order of DI. And when he works it through, then you need to grow on the lower hybrid time scale, something like 10 omega LH. Okay? So, and then the condition you want is like gamma tau to be bigger than 1. So the upshot is if you're near the upper end of the lower hybrid range in terms of growth rates, you can probably beat it easily. But if you're further back down towards an ion cyclotron time, it's going to be tough to beat this. So that even if the instability wanted to be there, we think it's sort of flushed away before it can grow and do something. The time scales associated with these electron layers are very fast. Now, if you had a bigger system, and these layers indeed get longer, then it's gonna be easier to meet the time scale then. So maybe for, even if an instability, you don't necessarily see it in our smaller boxes where we're trying to push a huge mass ratio, if you could afford to do the larger system at big mass ratio and get a longer layer, then maybe it'll show up again. More bigger
That's the
signal.
issue, I remember that was Audrey Russell and Youngson in their analysis of the stability.
Oh, they
So
discussed
there was
this.
there was a stability, it was growing, but then if you look at how much it would be able to grow before being affected, it was a problem.
Now, what you would really prefer is to have an instability that's pinned to the electron time scale. Then you'll always win, it looks like. Yeah.
That's the advantage of well, of course, are you pretty convinced that this instability you've been looking at requires coupling to the ions?
Well, like we say, we've done it over, this characteristic wavelength, intermediate between ion and electron scales. That's over
Does involve the
a big
ions.
range of temperatures and a big range of mass
So
ratio.
it seems to involve.
And it seems to involve the ions. Yeah, but it would be interesting to see how much higher frequency your instability is, really where it falls in comparison to this. Because you can see from his frequency, his power spectrum he was showing there's definitely not instabilities at higher frequency in ours. So basically, you've pretty much heard all these conclusions. The final thing here, let me just mention, is that even if it turns out that near the X line it's hard to balance or to break the frozen-in condition with these fluctuations, we have seen evidence in the 3D that these fluctuations may trigger the formation of secondary islands or flux robes. So I think the issue of the flux robe formation in 3D is probably going to be connected to any other instability that might want to exist in that layer. The other instabilities can break it up and start seeding something, and then maybe the secondary reconnection instability would take over. But for those again, you tend to see them in larger systems where you allow time for some expansion in the outward direction. So that's about all I had to say.